Greetings. My name is Yoav, and I'm the team captain of the Reali Drone Program team from the Haifa Reali High School. Today, I will guide you through our technical design and flight readiness review. But first, let's introduce our team. Yoav Pas Friedman, which is me, Ronel Tardi Ovadia, Maya Baitman, Ofri Naftali. Here is our development team. Finally, here is our safety pilot and advisor. Our UAS is very powerful and is suitable for doing a full mission demonstration this year. With a capability of 1 hour of flight time with 5 kg payload, we are very confident of doing our mission successfully. Technical design. In order to pass the acceptance criteria, we had to consider what is in our scope of criteria. Our drone is designed and can fly around 13 miles in no more than 30 minutes with 5 kg of payload. Our base system is the DR-1200 quadcopter. Our system is capable of flying via given waypoints, drop bottles using a mechanism developed by us, recognize objects whether they are emergent or standard, and avoid static and dynamic obstacles. Design overview. Our system consists of 4 main operators: safety pilot, team captain, ground station operator, and imaging operator. The imaging operator has another laptop which receives the images from the drone and autonomously detects the object. Then, the object is being sent autonomously from the imaging laptop to the UAV. We chose the Sony Alpha 6100. This camera is capable of taking up to 24.2 megapixels. The ISO, which is the sensitivity of the camera sensor, is ranging between 100 and 32,000. In order to maximize the recognition potential, we had to choose this camera, which has a very high clarity. As we know, this year the objects have been resized and made smaller, which resulted us into choosing this camera in order to maximize our chances of recognizing an object. In order to identify our objects, we use 2 separate algorithms. In order to recognize an emergent object, we use the YOLO model, which can recognize the mannequin. In order to identify the standard objects, we first trained one neural network in order to recognize the shape. Then, we pass the picture into the tesseract module, which can recognize which letter is in the object. Finally, we pass the image through an image segmentation algorithm, which can tell us how many % of presence each color has in its picture. Finally, we can determine the color of the letter and the color of the shape. The payload which our drone will drop are the water bottles that need to land safely on their given target. Altogether, our mechanism works as the following. A plastic head to the bottle is positioned on its upper portion, securing the bottle on it, and the soft sponge is attached with a rubber band to the bottom of the bottle for a safe landing. A horizontal slot and a chamber are located on the plastic head. The first has a place for a servo arm to be inserted into, and therefore hold the bottle from falling. The second is a place to store the parachute while in flight. The servo is located on a part that is secured firmly to the rest of the drone, and which holds the plastic head and subsequently the bottle in place during the flight. The servo arm is the sole part of the mechanism that restricts the bottle from falling. Once the drone decides to dispense the water bottle, it rotates the servo arm so as not to be in the way of the plastic head from falling. The head, subsequently, slides together with the bottle towards the ground. While falling, due to air pressure and drag, the parachute erupts from its now open chamber and halts the bottle's ever-accelerating dive towards its target, ensuring a safe landing. The hardware that we use in order to communicate with our ground station includes three components. The first component is the RFD900X, which is a long-range radio modem in order to communicate with our autopilot through a ground station software, Mission Planner. The range of the modem is estimated for almost 40 kilometers. The data transfer rate that we use is 57,600. The modem link is encrypted with WPA2-AES encryption, which provides a high level of data protection. Our second component is the 5.8 GHz Wi-Fi link, which is provided by the ground-based Ubiquiti NSM5 directional antenna. The UAS is equipped with an Ubiquiti bullet module. We use a protected point-to-point communication channel, which allows only permitted ground stations to communicate with our UAV. Our third component is the radio controller, which is transmitted over 2.4 GHz with the Archer R8 Pro and used for manual control. The aircraft consists of four motors. Each motor is connected to a 30-inch propeller. The aircraft's total weight is 20 kilos. The battery configuration consists of four LiPo batteries. Each has a capacity of 1600 mAh and 7 cells. Each pair of the batteries is connected in series, while the two pairs are connected in parallel. The airframe is made out of carbon fiber, stainless steel, and 3D printed ABS. The autopilot that we chose for our unmanned aerial system is the Pixel Cube Orange. The cube consists of three IMU sensors, 32-bit ARM processor, integrated accelerometer, gyro, barometer, and a magnetometer. In order to map our competition tasks using our autopilot, we use the open source ground station mission planner. In order to program our UAS and uniform it what waypoints it needs to go within, we use Mission Planner to enter the waypoints. In order to tell our autopilot where to go when recognizing an object, we use the MAV proxy tool to connect between our autopilot and our Raspberry Pi. In order to avoid obstacles and other aircrafts, we equipped our drone with a rangefinder LiDAR. In our case, the SF-45B from Lightwear. The SF-45B can scan up to 40-20 degrees. It can detect objects up to 50 meters away from the sensor itself. During the development of our dropping mechanism, we tried multiple versions. Some have failed and others succeeded. For example, one mechanism was using a solenoid. But this mechanism didn't work because the solenoid wasn't strong enough. Another example is gear-based mechanism, which also failed due to the setup time needed to install each bottle. During the software development, we also had a few alternatives which were considered. For example, an algorithm based on the OpenCV library was considered, but due to its inaccuracy, it was not good enough for our needs. While developing our UAV, we encountered a few risks that can happen during the mission. In this section, we will describe them and how we migrated them. The first risk that we encountered was flight determination. In order to secure our systems and surroundings as best as possible, we needed to program our drone to conduct a failsafe whenever the RC was disconnected from the UAV. The second risk that we met was that our detection algorithm might not work. To resolve this problem, we connected to our UAV a 5.8 GHz Wi-Fi link in order to transfer images to the ground station. The third risk that we needed to deal with was not using a fast deployment. At first, we thought about a dropping mechanism which was very effective, but it was not safe enough and it would get to the ground at very high speeds. In order to fix this problem, we connected a parachute to each one of the bottles in order to land more gently. Flight Readiness Review. In order to test our algorithm, we needed to create a dataset. We created a dataset with over 1,000 images. After feeding our algorithm the dataset, we found out that the accuracy was 97.3. The average resolution for each object was about 100 by 100 pixels. In order to ensure the best image quality, our team needed to adjust the sharpness, exposure time, and zoom amount of the camera in order to get the best image quality as possible. The tests that we have performed on our mechanisms are the following: payload drop from a high building, mechanism stability while doing sharp turns with the drone, payload drop from the drone, mechanism ability to release while experiencing irregular movement or pressure. The results were the following: as of 24 attempts, 19 were successful, meaning the parachute opened. The bottle landed without any deformations, and the bottle landed within 15 feet of the target. The 19th percentile distance from the target was 4.1 meters, or 13.4 feet. In order to test our communications systems and their performances, we conducted a few tests. First, in order to test the telemetry link, we tested it on the ground, then in flight. The RC receiver and Wi-Fi link were also first tested in ground, then in flight. The maximum range of the telemetry link that we tested was 4 kilometers. The maximum range of the RC receiver that we tested was 2 kilometers. The maximum range of the Wi-Fi link that we tested was 4 kilometers. In order to make sure that our UAV can fly the desired distance in minimum time, we have conducted 40 flights. During these flights, our UAV passed via a total of 1,400 waypoints. The total flight time was 19 hours. In a total of 40 flights, we conducted a total of 30 flights which were autonomous. The average manual mode per flight was 20 seconds. The number of waypoints attempted was 1,400 waypoints. The number of waypoints hit was 130.75. The average waypoint miss error is 1%. 0.7. In order to test our obstacle avoidance, we tested it in our mission testing. At the start, we tested our obstacle avoidance while flying the drone manually. After about 6 tests, we were ready to switch to autonomous mode while trying to avoid obstacles. Our UAV avoided a total of 150 obstacles in autonomous mode. The full mission tests that we have done were successful mostly. In total, we have done 10 full mission demonstration flights. The highest score was 100%, while the lowest score was set 67. The average score was 85.9%. This year, we are more than ready to compete in SUAS. Our test flights and imaging processing accuracy got us the confidence of making sure we are ready and prepared for this year's competition. We have conducted a plethora of mission tests and training in order to make sure we are confident enough to attempt and succeed in our mission demonstration. Lastly, we want to thank Dronix and Ready Eddy for sponsoring and helping us to make our dream come true. Now, we will present to you our proof of safe flight videos.